Alright, so we're well into Chapter 5 now, at least with the ionic compounds. So at this point we're going to make things a little more difficult. Up until now we've talked about binary ionic compounds. Two elements involved, a metal and a non-metal. And hopefully things have been getting comfortable there. If you're not already at the level where you're really comfortable with them, you're at least becoming used to the idea of metal and non-metal. And the metal can sometimes give you trouble if it has more than one stable ion, and that's about all that we've thrown at you in the way of a curveball yet. Alright, so now let's see what happens when the non-metal gets a little complicated. So far the worst we've seen is the metal having an opportunity for two or more stable ions, and we have to handle that with Roman numerals in the naming. Now we're going to look at what happens when we have more than one non-metal ion. Or at least non-metal element present in the anion portion of the substance. Okay, so polyatomic ions, it's a group of atoms. It has an overall ionic charge. That's the charge spread across that group of atoms. And the common examples we see here, there's just the one common cation, ammonium, NH4+. Everybody else is a minus, and ammonium behaves a lot like potassium. So if you can think potassium when you see ammonium, you'll be in good shape for a lot of the things that we'll talk about later, like solubility rules and things like that. So ammonium's the one time that we could have something replace a metal, and therefore we could end up with an ionic substance that has no metals in it. So this does complicate things a fair bit if you've gotten used to the idea of an ionic substance being a metal and a non-metal. Well, now we've got ammonium, which behaves a lot like potassium metal, but it's not a metal. It's nitrogen with 4 hydrogens and a net positive charge, and it does give rise to the one time we could see a formula for an ionic substance that has no metal at all. The others, nitrate, carbonate, hydrogen carbonate, which is still referred to by the biologists as bicarbonate, but we've ditched that name in chemistry. We prefer hydrogen carbonate. That's our modern naming, but you'll still see bicarbonate a lot, and things like sodium bicarbonate, or sodium hydrogen carbonate, as we should call it, baking soda. You'll still often see that called bicarb or bicarbonate. The hydroxide will become very important as we talk about acids and bases. And then nitrite, phosphate, these are the common ones. Notice we have nitrate and nitrite, and that's going to potentially cause some problems if you're not very careful with your spelling or with your writing, if you confuse nitrate and nitrite. Okay, so the polyatomics, the common ones will often end in ate for you, so we saw nitrate and phosphate. If you take one oxygen away, you end up with the ite ending instead of the ate. So NO2 minus is nitrite, whereas NO3 minus was nitrate. And PO3 3 minus is phosphite, whereas PO4 3 minus was phosphate. So notice we haven't changed the charge, we've just changed the number of oxygens and therefore changed the name. If we have hydrogen attached, we use the prefix hydrogen or bi. So HCO3 minus is hydrogen bicarbonate. Either hydrogen carbonate or bicarbonate. Don't mix them up. Officially, according to the International Union of Pure and Applied Chemists, the official name is hydrogen carbonate, but you'll still see bicarbonate quite a bit in that example. For HSO3 minus, that's hydrogen sulfite, also known as bisulfite. Of course, if you didn't have the hydrogens there, carbonate would be CO3 2 minus, sulfite would be SO3 2 minus, and you would just use the regular naming rules there. So here we see table 5.7, the names and formulas of some common polyatomic ions, and these are really the ones that you should know. It would be great if you could commit all of these to memory. You don't have to memorize all of them if you know the tricks. Hydroxide and ammonium, those two you probably do have to just do some straight memorization. But if you know nitrate, then you would know that NO2 minus would be nitrite because it's just one less, and we said the trend is if you remove an oxygen from something that ends in ate, it now becomes ite. If we look at chlorate, the bolded one there, when we're dealing with chlorine-based polyatomics, if we add an oxygen to an ate, we get a per 8. So if we take ClO3 minus, which is chlorate, we have ClO4 minus would be perchlorate. If we were to take and go the other direction, take an oxygen away from ClO3 minus, we have ClO2 minus, which is chlorite. So just like nitrate to nitrite, chlorate to chlorite, and then we could take even another oxygen away, and we have hypochlorite. So that shows us an example of what we can do when we have the possibilities to add or remove oxygen, in this case multiple oxygens. If we replaced Cl with Br, we would have, if it was BrO3 minus, we'd have bromate, and then we could have bromite and hypobromite and those sorts of things. So once you know one, you got a handle on a lot of the variations that you might encounter in other courses. For carbon, we have carbonate, and then if we add a hydrogen there, we have now hydrogen carbonate. Notice adding that hydrogen also decreases the charge by 1. So carbonate is a 2 minus, HCO3, hydrogen carbonate or bicarbonate is just a 1 minus. Cyanide is another very toxic but possible polyatomic with carbon now being bound to nitrogen as Cn minus 1. And then finally acetate, relatively harmless polyatomic after speaking about cyanide here just a moment ago. Acetate is H2C3O2 minus. For sulfur, we have sulfate, SO4 2 minus rather, sorry. And then we have hydrogen sulfate or bisulfate, which is HSO4 minus, or we have, again, notice that that's additional hydrogen and one charge less, just like going from carbonate to bicarbonate, or hydrogen carbonate going from sulfate to bisulfate or hydrogen sulfate, we go down by 1 after we've added that hydrogen. Sulfite, SO3 2 minus, again, if SO4 2 minus is sulfate, then if we take an oxygen away, we form sulfite. And finally, we could do the same sort of thing we did with hydrogen sulfate or bisulfate, we can do with hydrogen sulfite or bisulfite, and notice it also decreases the charge by 1 when we add that hydrogen here. Finally, the phosphorus-based ones, we have PO4 3 minus, that's phosphate, and if we add a hydrogen to it, it's hydrogen phosphate. The phosphate was a 3 minus, hydrogen phosphate is just a 2 minus. If we do another one, dihydrogen phosphate, now we're down to 1 minus. And then finally, if we forget about the hydrogens and just take PO4 3 minus and take an oxygen away to get PO3 3 minus, we go from an 8 to an 8, as you're probably already used to. Okay, so these are a good list of polyatomics to commit to memory, and if you can do that, then you can really handle variations quite well if I give you bromate instead of chlorate, for instance. Alright, so having polyatomic ions present doesn't really change our overall process for figuring out an ionic compound, right? The polyatomic would have to have an oppositely charged ion, either a single ion or another polyatomic. So as we said, NH4 plus ammonium ion is our really only positively charged polyatomic we deal with in the course. So that would have to be associated with either another polyatomic that's negatively charged or some monatomic negatively charged species like chloride or bromide, for instance. If we've got the negatively charged polyatomic, those other ones, we'd have to have either ammonium ion or a metal ion associated with it. So we form ionic bonds by having those opposite charges pair up in such a way that we get a net neutral charge. And if we look at our example here, if we have calcium ion as our cation and nitrate ion as our anion, well, the calcium's a group 2 or 2A, it's going to form a 2 plus ion. The nitrate is a -1, so when you memorize the names, please also memorize the charge, because it is important that you know nitrate's a -1. So if we have a 2 plus from the calcium, we'll need 2 of those -1 charges to get a neutral species overall, and therefore we'd have to have calcium nitrate. Notice the naming, writing the English words, calcium space nitrate, that should be no problem, but when we have more than one polyatomic, in addition to the subscript after it, we keep it in parentheses to make it very clear that that nitrate is a unit. So we have 2 nitrate ions. We can't just put a 2 after the nitrogen and a 6 after the oxygen. That's not legitimate. We need to show that that polyatomic ion is stable on its own, and the way we do that is by putting the polyatomic in parentheses and then putting a subscript afterward. If it's just one, if we were dealing with, say, ammonium chloride, NH4Cl, we don't have to put it into parentheses. But if we are dealing with multiples of a polyatomic ion, we always put the polyatomic itself in parentheses, and then after the end parenthesis, we put the subscript to indicate the number of that polyatomic. If we look at table 5.8 here, we have some compounds that contain polyatomic ions. So as you see, barium sulfate. The sulfate is not in parentheses because it's a 1-to-1 ratio of barium ion to sulfate ion. Same deal with the calcium carbonate. If we look at calcium phosphate, on the other hand, there's multiple phosphates required to correctly charge balance the calcium because you have a mismatch. In the case of the barium sulfate and the calcium carbonate, everything was +2 and -2 for the metal and the polyatomic. Here, our polyatomic phosphate is a 3-, our calcium ion's a 2+. We're going to have a subscript for each. We need 3 of those calcium 2+ to equal out 2 of the phosphates at 3- each, and the calcium doesn't need parentheses, but the phosphate, the polyatomic, gets parentheses around it before its subscript. And the rest I'll leave to you to look at, but obviously you'll notice that wherever we have multiples for a polyatomic, we have the polyatomic in parentheses. If the polyatomic is just a subscript of 1 that we don't show, we also leave off the parentheses as well. Alright, so we've gotten used to these guides. So now we have a guide here on this slide to naming ionic compounds with polyatomic ions. So first we will identify the cation and polyatomic ion, the anion, and again it could be a polyatomic cation if we're dealing with ammonium ion, but most of the time we're dealing with anionic substances for the polyatomic. The second step, name the cation using a Roman numeral if needed. So if it's a transition element other than zinc or cadmium or silver, if it's a main group element that appears in lower group 4A or 14, tin or lead, we'll need it. But again, be careful, because to put it there when it's not necessary is just as wrong as to leave it out when it is necessary. Step number 3, we'll name that polyatomic ion, and then step number 4, we'll write the name for the compound, cation first and anion second. Again, it could be a polyatomic cation if we're dealing with ammonium ion, or more likely it's going to be a polyatomic anion. But just be careful, if it was a Roman numeral needing metal ion as the cation, be sure to include that Roman numeral in parentheses as well as the name. Alright, so let's work this one together. So we have K2SO4. So right off the bat, hopefully you recognize that you're dealing with one metal and 2 nonmetals. So that means we must be dealing with a polyatomic. When we see more than 2 elements total, we know there's a polyatomic somewhere if we're dealing with a neutral ionic substance. And so we can identify the cation and the polyatomic ion, the anion in this case. So the cation is K+, the anion is SO4 2-. Right? The potassium, as long as you know that that's a +1, that can help you with the charge, but that's not always going to be the case. So it's really critical that you memorize the charge as well as the formula and name for those polyatomics, the common polyatomics from our table. Step 2, name the cation using a Roman numeral if needed. Potassium's a group 1 or group 1A metal. No need. It's always going to be a +1. It would be wrong to have the Roman numeral here. Step 3, name the polyatomic ion, and this is from memorization, so you know that SO4 2- is sulfate ion. Finally, in step number 4, write the name for the compound, cation first and polyatomic ion second. So potassium space sulfate. And there it is. It's just that easy. You're going to get a chance in a moment to convince me of that when you try your learning check. Okay, so in this learning check, you're going to match each formula with the correct name. So they might be right across from each other. They might be at a diagonal. It's up to you to decide. So for number 1, we've got MgS, MgSO3, and MgSO4. So using those choices A, B, and C, pair the correct letter with the correct formula. Same thing for number 2. Now we're dealing with calcium as opposed to magnesium in the first part. All right, pause the video now and start it up when you're set. All right, here we are. So MgS is actually C, magnesium sulfide. For MgSO3, that's actually choice A, magnesium sulfite, and MgSO4 is B, magnesium sulfate. And hopefully you could, even if you didn't know it thoroughly yet because you haven't had enough practice, you could recognize that the 8 is going to be the one with the more oxygens, the ite is going to be the one with fewer oxygens, and the ide is the ending for just the binary sulfur as an anion. For number 2, Ca parentheses ClO3 close parenthesis 2 is calcium chlorate, so choice A. CaCl2, hopefully that was the easy one, calcium chloride. And then finally Ca open parenthesis ClO2 close parenthesis 2 is B, calcium chlorite. And again, the 8 has the more oxygens in the polyatomic, the ite has one less. So hopefully that helped you if you were struggling with that concept. The exam will be multiple choice, so you will be able to hopefully get some help from the answer choices themselves in order to identify the correct answer choice on exam 2. Alright, looking here at the next learning check, now we're going to name each of the following compounds. So this time you don't have the multiple choice answers to help you. You're just going to take the element symbols and come up with the names for 1, 2, and 3. I won't say any more because I can't help but give away things if I keep talking, so please pause the video now and start it back up when you've made your naming assignments. Alright, so step 1, identify the cation in the polyatomic anion. In these cases, of course, remember there is the ammonium ion for polyatomic cation, but usually we're dealing with polyatomic anions. So we have the copper, lead, and barium as the cations for these 3 compounds. For the first one, the polyatomic is ClO3-, the second case it's CO3-2-, and the third case it's PO3-3-. Moving on to step 2, we have now the name the cation using a Roman numeral if necessary. So in the case of copper and lead, it is necessary because copper is a transition element that's not silver, zinc, or cadmium, and so we need to name that as copper, open parenthesis, Roman numeral 2, close parenthesis. How did we figure out the 2? Well, we know that ClO3- is a singly charged anion, and therefore we have 2 of that polyatomic anion, so it's a 2-, so we need copper to have a 2+. For the second case, lead, yes, we do need the Roman numeral because lead and tin are 2 main group elements, the only 2 in this course that I'll hold you to, that do need their cation name to include a Roman numeral. So in this case, because we know carbonate is CO3-2-, we know that the lead is 2+, and that's how we know to say lead 2 as opposed to lead 4 for the cation name. Finally, the last case is the easiest, barium, main group metal, not in the lower group 14 or 4A, so we can trust that barium will only form +2 ions, being a lower group 2 or group 2A element. Okay, and finally we're naming the polyatomic ions, so hopefully you've already gotten the hang of these and you know them by heart. If not, please do spend some time with that table and just make flashcards, however you memorize. That's one of the times I'll ask you to memorize. I try not to do a whole lot of memorization. I like you to be able to reason things out and use your understanding, but here there's just no substitute for rote memorization of those polyatomics. So the ClO3- one is chlorate, the CO3-2- is carbonate, and the PO3-3- is phosphite. And finally, here with step 4, write the name for the compound cation first and the polyatomic ion second, because in this case we're dealing with all anions for the polyatomic. So we have copper 2 chlorate, lead 2 carbonate, and barium phosphite. Hopefully that went well. If you're still struggling, again, it's pretty new, you're going to need some practice. Please try on your own first. If it's really not coming together for you, then certainly reach out to me for some help. Alright, so a simple guide to writing formulas for compounds with polyatomic ions, right? We did the naming from the formula just a moment ago. Now let's figure out how we're going to write the formula from the name. So first, we identify the cation and the polyatomic ion, which is usually an anion, and the cation is usually another metal, but do be on the lookout for ammonium. It will come up. Number 2, balance out the charges. And then finally, number 3, write the formula, cation first, using the subscripts from the charge to balance. Okay, so let's work one together. For our example, we'll use aluminum hydroxide. So based on that name, let's go ahead and write its formula. So from the name aluminum hydroxide, and be careful, ammonium and aluminum look a lot alike, so be very careful about that come exam time, because I've been known to offer those options for people who might mistake aluminum and ammonium. So step number 1, identify the cation and polyatomic anion in this case. So aluminum is the cation, Al3+, it's in group 3A or group 13, forms a 3+ ion. And then OH- is the polyatomic hydroxide ion. Step number 2, we'll balance out those charges. So we get 3 positive charges from the 1 aluminum ion. That means we're going to need 3 of the hydroxide ions to get a total of 3- and a net 0 charge. Now finally, we're at step 3. We're going to write the formula cation first using subscripts from the charge balance. So in this case, there was just 1 of the aluminum 3+ ions, so we'll just write Al, the symbol for aluminum. There are 3 of the hydroxides. Because hydroxide is a polyatomic, we're going to need to put it into parentheses, and because we need a total of 3 of them, following our end parenthesis, we'll put a subscript of 3. So we don't show the subscript of 1 for the aluminum, but we do have to show the subscript of 3 for the hydroxide and put it in parentheses. If there's just 1 of the polyatomic, then we show no subscript, no parentheses. Alright, so now it's your chance to see how you're doing. We have a learning check here with some names and some multiple choice options. And so from each of these 4 names, if you would select the one correct answer choice, go ahead, pause the video here, select your best answer, and then start back up to see how you did. Okay, so hopefully for aluminum nitrate, you went through our steps, and at the 3rd step, you ended up with the formula Al, open parenthesis, NO subscript 3, close parenthesis, subscript 3. That's the correct choice, choice C. Notice choice B had NO, but without the 3 there to make it nitrate. It just had the 3 after the parenthesis to make it the 3 quantities of the substance. So be very careful, read extra carefully, especially on those exams where you only get 1 choice, and once you've submitted, you don't get a chance to go back. Please read carefully. Number 2, copper 2 nitrate. Be careful. A lot of students are tempted to make 2 a subscript for copper. Copper 2 indicates that it's the copper 2+ ion, which means we actually need a subscript here for nitrate, because nitrate's only a -1. So to balance that copper 2+, we need 2 of the nitrate 1-. So choice B was correct there. And then number 3, iron 3 hydroxide. So hydroxide's the OH-, the iron's 3+. We're going to need 3 hydroxides to balance, giving us choice C. And finally, tin 4 hydroxide. We're going to have choice A, SN, parentheses, OH, subscript 4. Alright, so hopefully you're getting the hang of it. We're going to do another learning check right now to make sure we're all on the same page, and then hopefully if you're continuing to struggle, you do some additional practice problems and ultimately reach out to me if you're still not mastering the concepts. Alright, so in this learning check, you'll write the formula for each of the following. So here you don't have the multiple choice to help you. You've got to come up with it on your own. For number 1, calcium nitrate, 2, iron 2 hydroxide, 3, aluminum carbonate, 4, copper 2 bromide, and finally 5, lithium phosphate. So please pause the video, work those 5 names into formulas, and then start back up and we'll see how you did. Alright, so here we have it. Number 1, calcium nitrate, the calcium ion, nitrate polyatomic ion, calcium's a 2+, nitrate's a 1-, so you need to have Ca, and then open parenthesis, NO3, close parenthesis, quantity 2 to charge balance the 2 pluses from the calcium. Iron 2 hydroxide, very similar, the iron symbol, then in parentheses the hydroxide, and finally a subscript 2 because you'll need 2 hydroxides for the 1 iron. The aluminum 3+, carbonate 2-, we're going to have to swap those charges as subscripts, and we get Al2 parentheses CO3 subscript 3 afterwards to indicate a quantity of 3 carbonate ions. Copper 2 bromide, nice and easy, no parentheses here. Copper Br sub 2. There was no polyatomic present, but there was the variable charge possible on the copper, so we had to have Roman numerals in the name, but the formula looks very normal. Finally, lithium phosphate. Lithium's a 1+, group 1A metal, and phosphate's a 3-, so therefore we need 3 lithium 1+s for that phosphate 3-. Notice in the formula we do not have phosphate in parentheses because it does not have a subscript that's shown. All right, hopefully things are coming together. You're following along and it's just clicking. If that's not the case, please do some additional practice problems. Practice may not make perfect, but it certainly helps. And if it's not getting any better or you're still struggling, please do reach out to me for additional help. Otherwise, for good or for bad, we're done with the ionic portion of Chapter 5, and we'll pick back up with subsection 5.5 and start to deal more with those covalent bonding types.